Welcome back to Bargaining in War. In this lecture, we're going to solve for the corner solution of the game with incomplete information over the costs of war. Our ultimate goal is to examine how changing the valuation of the prize affects the frequency of fighting. To do that, to conduct a comparative static, we first have to have a solution. And so that's what we're going to be working on here. The game is exactly the same as we saw last time. Nature begins by drawing B's cost of war as a high quantity with probability Q and a low quantity with probability 1 minus Q. Only B observes the draw. A, in the dark, demands X between 0 and 1, and B, who again is fully informed, sees that demand and accepts or rejects it. The difference here is that last time we assumed that both the high and low cost types had positive values for war. Hence, it was the interior solution. This time, however, we're going to assume that the low cost type has a positive value for war, but the high cost type has a negative value for war. In other words, 1 minus P minus CB prime over VB, the high cost type's war payoff, is less than 0. Meanwhile, 1 minus P minus CB without the prime over VB is greater than 0. It has a positive war payoff. Well, from here, the algorithm that we're going to use is very similar to what we were doing the last time we had to solve for a corner solution in a game with incomplete information. This is good. We have some leverage on how to do this already, and we're going to reinforce this process so that when you have to do it yourself, you have some knowledge already about what to do and how to go about solving this sort of problem. Our first step is always to work backward, which means figuring out what each type of B is going to do in this situation, whether it's going to accept or reject a demand. Let's think about what the high cost type is going to do. If it accepts, it gets 1 minus X as its payoff. It's willing to accept as long as 1 minus X is greater than its war payoff, which is 1 minus P minus CB prime over VB. Well, we just realized that we're looking at the situation where the war payoff for the high cost type is negative. 1 minus X is constrained between 0 and 1. It is going to be at least 0, if not positive. So this relationship always is true because the right-hand side has to be negative. In other words, because the high cost type has a negative value for war, it accepts every demand that A could possibly make. The low cost type is not as easygoing. It also receives 1 minus X as its payoff for accepting, but its war payoff of 1 minus P minus CB over VB is a positive quantity, as we assumed here. So when we solve for X, X has to be less than or equal to P plus CB over VB for the low cost type to accept. It is willing to reject some demands if those demands are too large. So we now have figured out what each type of B is going to do. Let's use that information and think about the different types of X's that A can choose from and figure out which of those is optimal for it. And like the last time we were looking at a corner solution, this is a little bit easier than looking at the interior solution. So if we draw a number line and we think about this as the various types of X's that could be chosen by state A, remember there's a cap on it of 1, and we have this cut point here that we should draw out. P plus CB over VB. Implicitly, there's another cut point here that's really, really high that corresponds to the high cost type. This is greater than 1, however, and as a consequence of that, any demand that A might make is something that the high cost type is going to accept. Whether the low cost type accepts or not depends on where we are in relation to this cut point. Anything less than or equal to that cut point is something that the low cost type will accept. So both types accept here. In contrast, if we exceed that quantity, well, the high cost type accepts. Again, because it's accepting any demand whatsoever. But the low cost type rejects. So we have two different sets of demands that we have to look through to figure out which is the best for A. What is going to maximize A's utility? Let's first start off by thinking about some demand here. Something less than P plus CB over VB. Well, if both types are accepting, A's utility is X, the size of the demand. But we know that this type of demand cannot be optimal. Think about what happens if A were to increase its demand by some epsilon quantity. Well, both types are still accepting, and now A, instead of just getting X, is getting X plus a little bit more. This logic holds all the way through. You can keep adding epsilon more. So none of those sorts of demands could possibly be optimal. Until you get to the cut point itself, P plus CB over VB. At that cut point, both types are still accepting. But if A tries demanding a little bit more, then B is going to reject if B is the low-cost type. So that's going to change the probability of war. That's going to make it a fundamentally different type of demand being made. So the optimal demand that has no risk, that is guaranteed to be accepted, is X equal to P plus CB over VB. That's only one type of option. Another option is going greater than P plus CB over VB, something like right here. Let's think about what A's utility is for that sort of demand. Well, with probability Q, A is facing the high cost type, and the high cost type accepts. So A's utility is X. With probability 1 minus Q, it's facing the low cost type, which finds such a demand unacceptable. That low cost type rejects, and A gets its war payoff of P minus CA over VA. Let's think about why this demand here is not optimal. Well, let's compare that to this demand here instead. In both cases, the high cost type accepts, and the low cost type rejects. That does not change this portion of the utility function. It does change, however, this portion of the utility function. The high cost type is accepting regardless. The difference here is that you're getting epsilon more by demanding an additional epsilon quantity. So none of these values can possibly be optimal because you could keep adding epsilon more and more and more and always get a little bit more out of the high cost type. This is true up until you hit the value 1. Once you get to 1, that is the most that 1 can possibly demand. We can't exceed it. So, if you want to make a demand that the high cost type will accept and the low cost type will reject, that optimal demand is going to be X equal to 1. Now let's figure out which of these two possibilities, the safe demand or the risky demand, is the best. Well, let's first think about what the utility for the risky demand is. We actually know that for any risky demand whatsoever, never mind the optimal one, this is the value for it. We now have an X value of 1, so we're just going to substitute X equal to 1 into that, and we have the finalized optimal risky payoff for A. That's going to be Q times 1 plus 1 minus Q times P minus CA over VA. And it's willing to make that risky demand. It wants to make that risky demand if the utility associated with it is greater than its utility for the optimal safe demand, which pays off just X equal to P plus CB over VB. The reason that that is A's utility is that both types are accepting. So A just receives whatever it is demanding. From here, all we need to do is work through this inequality and figure out when one of those is better than the other. Let's start off by simplifying what we have on the right-hand side. So let's FOIL out what we have here. And we'll see that there is a minor simplification that we can make. These p's cancel. everything else looks like it's not going to change. So from here, what we should do, like always, is put this in terms of Q. And what do we have? Well, let's pull this Q here. We have a minus QP. And we have a plus Q CA over VA greater than, we got to move this CA over VA to the other side. And now if we collect those Q's into a single value and have it be undistributed, then we get this. And we are just about ready to solve for this now. So if we look at this quantity inside of the parentheses, 1 minus P is always going to be at least 0, and CA over VA is always a positive value. So that means everything inside of the parentheses is positive. We don't need to flip the inequality when we solve for Q, and what we get is CA over VA plus CB over VB divided by 1 minus P plus CA over VA. And just to visualize that once more, same sort of situation where we have this Q value, and we have a critical cut point, which is this right here, CA over VA plus CB over VB, all divided by 1 minus P plus CA over VA, where if Q is above that cut point, then A makes a risky demand because it is gambling on the fact that the high cost type is relatively frequent. And in contrast, if Q is relatively low, then that high cost type is not very frequent. The low cost type is much more frequent. And so A prefers to make the safe demand instead. And that's the solution to the game. So we've now figured out the corner solution to what happens with uncertainty over costs. And in the next lecture, we can get to that comparative static that we wanted to conduct. Hope you enjoyed this. Hope to see you next time. Take care.